Welcome to our deep dive into this really strange world of quantum entanglement. You've given us quite a mix here: a NOVA documentary on entanglement, a Veritasium video all about non-Euclidean geometry, and then this documentary on the history of mathematics across different cultures.
Oh, yeah. Now it's a fascinating mix.
Yeah. At first glance, you might be thinking, how in the world do these things fit together? But trust me, by the end of this, you'll see how math can reveal some of the most unexpected connections.
It's always fascinating to see how seemingly, separate areas of knowledge can converge.
Absolutely. So let's start with that NOVA documentary, which really dives headfirst into this concept of quantum entanglement. Can you break that down for us a little bit?
Yeah, so imagine two particles linked in a way that even if you separate them by vast distances, they still instantly influence each other. That's entanglement, a phenomenon so bizarre Einstein famously called it spooky action at a distance.
Okay, spooky definitely captures it. But, if something's happening instantaneously, doesn't that break Einstein's own rule about nothing traveling faster than light?
Exactly. That's what Einstein, Podolsky, and Rosen argued in their 1935 paper. They believed entanglement showed that quantum mechanics was incomplete. They even had this amusing anecdote where Podolsky, with Einstein's consent, actually ran to the New York Times about their paper.
Oh, wow.
Which made Einstein so mad he stopped speaking to him.
Talk about academic drama. But the documentary goes on to say that experiments had actually proven entanglement is real, right? They're even addressing loopholes that Einstein might have used to dismiss it.
Right. One experiment used light from quasars billions of years old to ensure the randomness of measurements, making it almost impossible that the particles somehow prearranged their behavior.
So it's like using the universe's own history to test a quantum puzzle? Pretty clever. But here's the thing that always gets me. If entanglement is this bizarre, this counterintuitive, does it actually have any use outside of, theoretical physics?
And that's where it gets exciting. Entanglement is actually the foundation for technologies like quantum computing, which has the potential to revolutionize everything from medicine to materialist science.
Really?
Imagine a computer that can perform calculations in parallel thanks to entangled qubits. It's like having millions of processors working together simultaneously.
Okay, hold on. My brain needs a second to catch up here. We went from spooky action to superpowered computers. How do these qubits actually utilize entanglement?
Think of a regular computer bit as a coin that can be heads or tails, representing 0 or 1. A qubit is like a spinning coin. It can be heads, tails, or in a blurry state of both. And entangling these qubits connects them in a way that magnifies their computing power exponentially. It's like their states are linked even though they're physically separated.
So Google's 72-qubit chip, the one they're always talking about, that's basically 72 of these spinning coins linked together by entanglement.
Yeah.
Wow. I'm starting to grasp the connection, but it still feels like something out of science fiction.
It does.
It makes you wonder, are we living in Einstein's universe of, common sense laws? Or is this quantum reality something else entirely?
It makes you question the very fabric of reality, doesn't it?
It really does.
And this questioning of assumptions, this challenge to what we think we know, has happened throughout history. Let's look at how mathematicians went through a similar upheaval when they discovered non-Euclidean geometries.
So we've got entanglement kind of messing with our understanding of the universe at the tiniest level, and now we're going to look at how geometry got turned on its head.
Yeah.
Okay, I'm ready.
This Veritasium video is a great primer on how our assumptions about space can be totally wrong.
Okay.
For centuries, Euclidean geometry, the thing we all learned in school, was considered absolute truth.
Right.
But it all started to unravel with Euclid's fifth postulate, which deals with parallel lines. It states that through a point not on a given line, only one line can be drawn parallel to the first line.
I vaguely remember that. It always seemed way more complicated than the other postulates.
Mathematicians felt the same way. They struggled to prove it for centuries.
Really?
But instead of a proof, they stumbled upon something much more radical. Non-Euclidean geometries, where the fifth postulate doesn't hold true at all.
Wait, so there are other kinds of geometry where parallel lines don't behave the way we expect?
Exactly.
Give me an example, because my brain is stuck in straight lines right now.
So picture the Earth as a sphere. In spherical geometry, lines are actually great circles that wrap around the sphere. Think about, those long-haul flights from the U.S. to Asia.
Yeah.
They often fly over the Arctic, even though it seems out of the way on a flat map. That's because on a sphere, the shortest distance between 2 points isn't a straight line, it's a curved path along a great circle.
So those flight paths are actually following the rules of spherical geometry.
Exactly.
Okay, I think I'm getting it. But what about the other type, the hyperbolic geometry? The video described it as saddles on saddles, which made my head spin.
It's definitely the harder one to visualize.
Yeah.
Imagine a Pringle chip, that saddle shape, Now imagine infinitely many of those Pringles stacked and curving in on themselves. That gives you a sense of hyperbolic space.
Wow. Okay.
In this kind of space, you could draw an infinite number of lines through a point that never intersect a given line.
Really?
Meaning there are infinitely many parallels.
Wow.
It completely breaks our usual understanding of parallel lines.
Okay. My brain definitely needs a diagram for that one.
Yeah.
It's amazing how math can describe spaces that are so different from what we experience in our everyday lives. But, I mean, why should we care about these bizarre geometries? Are they just like mathematical curiosities, or do they connect back to the real universe somehow?
And that's where Einstein's theory of general relativity comes in.
Okay.
It explains gravity not as a force, but as a curvature of space-time itself. Picture a bowling ball on a trampoline.
Okay.
The ball warps the trampoline's surface, and if you roll a marble across, it'll curve around the bowling ball.
So massive objects like stars and planets are like the bowling ball, warping the fabric of space-time.
Precisely. And just like the marble's path is curved by the warped trampoline, light rays bend as they pass near massive objects. This bending of light is called gravitational lensing, and it's only possible because space-time itself is curved, a concept rooted in non-Euclidean geometry.
So without those mind-bending geometries, Einstein wouldn't have been able to explain gravity as we know it. That's mind-blowing. It's a perfect example of how math reveals these unexpected connections, like really pushing the boundaries of our understanding.
And speaking of pulling boundaries, let's delve into the documentary about the history of math across different cultures.
Okay.
It really highlights how this quest for understanding is a universal human endeavor.
I'm ready to explore. It always fascinates me how different civilizations approached math. Like it seems like such a universal language. But I'm sure there were some unique methods and perspectives along the way.
Oh, absolutely. Let's start with the ancient Egyptians. They were incredibly practical, and their mathematics reflects that. They developed this fascinating system of unit fractions, fractions where the numerator is always 1.
Unit fractions. So instead of writing like 2/3, they would write it as 1/2 plus 1/6.
Right.
That seems incredibly complicated for like everyday calculations.
It does sound tedious, but it worked for them, and they were able to achieve some incredible feats of engineering. I mean, look at the pyramids. And speaking of the pyramids, there's this fascinating story about how they may have used ropes with knots to create perfect right angles.
Ropes with knots, like some sort of ancient measuring tool?
Exactly. They would tie knots at specific intervals along the rope, creating segments of 3, 4, and 5 units. When they stretched the rope into a triangle with those side lengths that would always form a perfect right angle. It's a practical application of what we know today as the Pythagorean theorem.
That's brilliant. It shows they had a really deep understanding of geometric relationships, even without the formal, mathematical proofs we use today.
And then there's ancient Babylon. They had a base 60 number system, which might seem strange to us, but it had some unique advantages.
Base 60, that's so different from our base 10 system. What was the logic behind that?
One theory is that it stemmed from their way of counting using their knuckles and fingers.
Oh!
They had 12 knuckles on one hand and 5 fingers on the other, totaling 60.
Wow.
Plus, the number 60 has a lot of divisors, making it very practical for arithmetic.
So their number system was literally based on their anatomy.
Yeah.
That's a connection I never would have made.
Yeah.
And it's amazing how that base 60 system is like stuck with us. 60 seconds in a minute, 60 minutes in an hour.
It's a legacy that's lasted for millennia. But the Babylonians didn't stop there. They were pioneers in astronomy. And to track the movements of celestial bodies, they needed to work with huge numbers. This led them to develop the concept of place value in their number system.
Place value. You mean like how the 1 in 100 means something different than the 1 in 10?
Exactly. That concept might seem obvious now, but it was a revolutionary idea at the time. And the Babylonians were also among the first to explore the idea of 0 as a placeholder in their number system, paving the way for a truly groundbreaking concept.
0. That brings us to ancient India, where the concept of 0 as a number in its own right was fully developed. I find it fascinating how something that seems so simple was such a radical concept at the time.
The Indian mathematicians had this profound understanding of the concept of nothingness, or shunya, which had deep roots in their philosophical and spiritual traditions. This understanding allowed them to see 0 not just as an empty space, but as a numerical entity with its own properties.
So their philosophical worldview actually shaped their mathematical thinking. That's a connection I never would have considered. It's amazing how these different areas of knowledge can influence each other. And the development of 0 wasn't their only major contribution, was it?
Not at all. They made significant advances in trigonometry, driven by their fascination with the relationships between angles and sides in triangles. They even used their knowledge of trigonometry to estimate the distance between the Earth and the Sun.
Wow.
Pretty impressive for the time.
It's like they were mapping out the universe from right here on Earth.
Yeah.
That must be required an incredible amount of ingenuity and mathematical skill. What other mathematical marvels did the ancient Indians come up with?
They did groundbreaking work with infinite series, especially developing formulas for calculating pi.
Oh, wow.
They understood that even seemingly infinite processes could be understood through mathematical equations.
It really shows how math is this incredible tool for understanding the world around us, from the smallest things to the vastness of the cosmos. We've gone from spooking action at a distance to curved space-time and the development of zero. It's almost like we've been on this whirlwind tour of the universe, guided by the language of math.
And through it all, we see this human desire to understand, to push the boundaries of knowledge. From the ancient Egyptians building pyramids with ropes and knots to modern scientists trying to harness the power of entanglement.
Right.
It's clear that mathematics has been a driving force in human progress.
It's a testament to the power of human curiosity and our relentless pursuit of understanding the universe and our place in it. But before we wrap up this part of our deep dive, is there anything that particularly stands out to you from the history of math across cultures?
What fascinates me is how different cultures approached mathematical problems from such unique perspectives.
Yeah.
It's like they were all looking at the same universe but through different lenses. And those different perspectives enriched our understanding of math in profound ways.
That's a great point. It's like each culture added a new brushstroke to the grand masterpiece of mathematical knowledge. And with that, I think we're ready to move on to the final part of our deep dive. It's amazing to think about how far we've come in our understanding of math. Those early civilizations working with ropes and knocks to modern-day mathematicians grappling with concepts like entanglement.
It really highlights the cumulative nature of knowledge, doesn't it? Each generation builds upon the discoveries of those who came before, pushing the boundaries of what we know just a little bit further.
And sometimes those seemingly small steps lead to giant leaps in technology. Think about transistors, those tiny components that power all our electronics. I mean, they're a product of our understanding of quantum mechanics, and they've completely revolutionized the way we live.
Yeah.
It makes you wonder what future technologies might emerge from the research being done today on entanglement and quantum computers.
The possibilities are truly mind-boggling. Imagine a world with unbreakable encryption, personalized medicine tailored to your unique genetic code, and materials with properties we haven't even dreamt of yet. It sounds like science fiction, but these breakthroughs could become reality, all thanks to our ever-evolving understanding of the universe and the language of math that describes it.
Okay, I have to ask, if you could peer into the future, what's one advancement driven by these cutting-edge areas of math that you'd be most excited to see?
For me, it would have to be the development of a true quantum computer capable of solving some of humanity's biggest challenges. Imagine using a quantum computer to model, complex climate systems leading to breakthroughs in renewable energy.
Yeah.
Or tackling diseases like Alzheimer's by simulating protein folding at a molecular level. The potential for positive impact is just enormous.
It's almost like math is a key that unlocks these hidden doors to the future.
Yeah.
But even with all these advancements, there are still so many mysteries left to unravel, aren't there?
Absolutely. We've come a long way, but we're still grappling with these fundamental questions about the universe. What is the nature of dark matter and dark energy? Are there multiple universes out there? What is the ultimate fate of our own universe? These are questions that might take entirely new branches of mathematics to answer.
It makes you realize that we're still just scratching the surface of what's out there, of what we don't know.
Yeah.
So as we wrap up this deep dive into entanglement, geometry, and the history of math, what's the one big takeaway you'd like to leave our listener with?
More than anything, I think this journey highlights the importance of curiosity. Never stop questioning, exploring, and seeking out those unexpected connections.
Yeah.
The universe is filled with wonders, and math is the language that helps us understand those wonders, revealing hidden patterns and opening doors to new possibilities.
It's like that famous saying, the more I learn, the more I realize how much I don't know.
Right.
And that's a good thing, right?
Yeah.
It keeps us hungry for knowledge, pushing us to explore further. So to our listener, keep that spark of curiosity alive. Keep exploring, keep learning, and who knows what incredible discoveries you might make. Thanks for joining us on this deep dive.